All right, well, good morning, grade nines. Yeah, I guess I'm talking to cohort A today. Okay, so cohort A, good morning. I'm glad to see the STEAM technology Slack channel is very busy. I'm going to apologize if I don't get to a question. Honestly, you guys are doing a good job of answering each other's questions. And I might miss something because there's so many posts. That's all right though. Like I think you're keeping it relevant, so it's good. It's what it's for. So if you're really stuck though, and I miss something, just remind me because I don't. Sometimes I just quickly scroll through it, and if I feel like you've answered each other's questions, then I don't answer it. Okay, so maybe I missed it, and if that happens, just let me know. All right. Actually, I wanted to. There's a little. Remember, I was telling you we did a little hearing test today in class, like this, or sorry, yesterday in class when you were in person. We did a little hearing test towards the end, and I said that we would do that today. Before we get there, though, let me just go back to OneNote. All right, we're going to do one lesson today, just one, and it's lesson number 6, where it says frequency and pitch, decibels and loudness, and speed of sound. So what I want to do is, we already talked about frequency and pitch, but maybe we'll get to it. Okay, here in just a moment. Let me go back to this. It says speed of sound here, so let me just zoom in on this in the notes. Speed of sound is a really quick thing, so let's do that first. Okay, we'll look at the speed of sound. All right, so sound travels really well. Like we've been talking about waves, right? We've been talking about waves here, but sound itself travels extremely well through media like air, okay? But it travels even better through more dense medium, like for example, water. Water is an amazing medium for sound. Solids are even better, okay? So here, to give you some sense of it, take a look at how fast sound moves through various things, okay? So here, I'm gonna start at the bottom where the speed of sound is the slowest. So I'm just a couple of highlights here. Meters per second, okay? Now, these are all numbers in meters per second, and to give you some sense of how fast this really is, 332 meters per second is the speed of sound at 0 degrees Celsius in air, okay? To convert that to kilometers per hour, to give you some sense of it, you times by 3.6, and you get almost 1,200 kilometers per hour. This is equal to, I don't know why I'm writing in red, but I'll still write in red. Okay, so 1,195, 95 approximately kilometers per hour. To give you some sense, okay? You might drive your car at, your parents drive your car at 100 kilometers per hour down the Queensway. So sound actually travels 12 times faster than that speed on the Queensway. So a cheetah runs at around 100 kilometers per hour on its fast bursts. Okay, sound is 12 times faster than that. It's very fast, and that's at 0 degrees Celsius. It actually gets faster with higher temperatures. We'll talk about that in a moment. Now let's take a look at some other things in hydrogen gas. So let's say you were, taking a visit inside the sun or something. Okay, it's very hot. Let's say it was cold hydrogen gas. Let's say it's like Jupiter, which is hydrogen and helium gas at cold temperature. Well, you can see here that sound travels around 1,270 meters per second. Okay, these are in meters per second. That's extremely fast. Okay, that is like 3,000, 4,000 kilometers per hour, roughly. Okay, so very, very fast. And, so it depends on the material itself. So oxygen, okay, 317 meters per second, carbon dioxide, 258. Of course, air is a mixture of mostly nitrogen and trace amounts of other gases. And so here we see that nitrogen gas is 350 at 20 degrees Celsius. That's very similar to air, because air would be around 343 at 23 degrees Celsius. So we can see that, since the air is mostly nitrogen, it's very similar to air. All right, now that's in gases, but what about in liquids? Well, take a look here, fresh water, so in a lake or something like that, 1,493 meters per second. That is amazingly fast, okay? So it's 1493 times 3.6. It's actually 5,000 kilometers per hour, 5,400 kilometers per hour. So extremely fast in water, way, way better than air, okay? Like much, much better than 350 kilometers per hour. So it's approximately 5 times the speed that it is in the air underwater. And so water is an excellent conduit for sound waves. Fresh water, a little bit slightly better than seawater, but it depends on how much salt there is. Okay, so I think the more salty it is, I don't know if that speeds it up or slows it down. I'm not 100% sure. Here they put a random thing, your alcohol, 1241. Liquids, though, in general, very good at conducting sound waves. Okay, here you have your brain. Inside your brain, sound waves will travel inside your brain very fast, okay, around the same speed as they do in fresh water. Now, in solids, it's take it up to a brand new level. Like look at this in aluminum, 5,104 meters per second, which is, let's do it, 5,104 times 3.6. That's like 18,000 kilometers per hour, okay? It's amazingly fast. And all of the solids have extremely high numbers, generally speaking, at least 10 times faster than they are in air. Okay, so gases are good conduits of sound. Liquids are better, and solids are the best by far at conducting sound waves. Okay, so sound is this longitudinal wave, travels through different media, solid, liquid, gas. Now, there is something missing from the list. I'm just going to say note in a vacuum. So if there's nothing, if you're just in outer space, I'm just going to say note. Sound does not travel at any speed. Sound cannot travel through a vacuum. The vacuum, pardon me, probably going to spell this wrong, the vacuum of space. Or any vacuum at all, but typically that's outer space, right? And so 0 speed of sound. It's funny, light is the opposite. Light travels very fast through a vacuum, actually. That's when it travels the fastest, 3 times 10 to the 8 meters per second. That number's come up before. Okay, but it actually slows down when it goes to more dense media. But sound and light, it's totally the opposite behavior. Sound is better in more dense media and slower in less dense media. And if you go to no density, if you're in a vacuum, it's 0. Like it just, sound does not travel through a vacuum. But light can. In fact, that's when light travels at its fastest speed. Okay, so that's how the speed of sound works in various media. Now, by the way, there's also an equation here. I'm just going to do an example. Okay, the equation speed equals distance over time. And for you triangle people, I've given you the speech on getting away from triangles, but you know I'm generous. I'm a generous man, so I will give you the triangle here. Speed equals distance over time, right? Now that's just a generic equation. You could measure the speed of someone running a 100-meter dash. It's distance over time, right? Just take how far they've run, divide it by time. That's their average speed. That's how it works. It's a very straightforward basic equation in motion, okay, when we're describing the motion of objects. It's a basic relationship between speed, distance, and time. Well, it works for waves too. And so here, let's do an example. Let's say you're in salt water. Let's say you're in the ocean. Okay, so salt water where the speed is on the chart here, 1470 meters per second. Okay, now, let's say you have a submarine that emits a sound, or a dolphin that emits a sound. Okay, how far would it go? So how far would a sound travel in 2.5 seconds in seawater? Okay, at this speed of 1470 meters per second. So this is a kind of a basic question. And all you have to do to find the distance is you go distance equals speed times time. It's the same formula. You can use the triangle or just rearrange this equation, solve it for distance by multiplying both sides by time. Trust me on this, get good at the algebra. Now we just plug the numbers in, 1470 times 2.5. I'll take out my calculator. So 1470 times 2.5 is 3,675 meters, which, if you want to convert it to kilometers, 3.675 kilometers. So that's how far sound would travel in just 2.5 seconds in the water. That's pretty far. Light wouldn't even make, or sorry, sound waves in air wouldn't even make it 1 kilometer in that same amount of time. Okay, so you see the difference, right? It just travels so fast in the water. And it travels, not only does it travel fast in the water, it travels well through the water. So you can hear a sound at extremely far distances underwater compared to air, which is a relatively poor conductor of sound. You don't hear sounds very far away from the source in air. Like you can't hear someone talking 1 kilometer away, but you can hear, if the sound is loud enough, you could hear 1 kilometer away maybe, but in underwater, you could hear even a relatively low intensity sound really far away from the source. Okay, and so that's it for speed of sound in various media. And don't forget, you can always use this formula in the questions in the homework for calculating speed, distance, or time based on the movements of waves, okay, in various media. Now, what about in air? Okay, so let's focus on air for a second. It varies with temperature. So it says in the chart above that at 0 degrees Celsius, the speed of sound is 332 meters per second. Now, this is specifically in air. Now, why is air so important? Well, I mean, that happens to be how you and I hear sound, right? Through air, okay? You're hearing the sound of my voice right now coming out of the speaker of your device. And like, that's transmitting the sound through air. So that is our, that is the story that humans find themselves in, right? We are adapted to listen to sound waves in air. So that's why we focus on this. For dolphins, we would focus more on the water, okay? But we're humans. So normally when we're listening to a sound, it's being conducted through air molecules. Now, how does it vary with temperature? So at any temperature in general, there's a formula, okay? And the formula looks like this. The speed of sound equals 332, so that's at 0. But it's actually better at higher temperatures. So the speed increases 0.59 for every 1 degree Celsius above 0. So T is this time equal to temperature. It's not the period or anything. It's not frequency and period this time. Whoops, this time, look what I did there. It's temperature. That's funny. I wrote tem period because I was saying the word period as I was writing the word temperature. In degrees Celsius, okay? V is the speed of sound. In air, in meters per second. Okay, so if I put in 0 for T, I get 332. That makes sense. Now, it works for negative temperatures, so I'm just going to say it works for winter temperatures, okay, negatives, and positive temperatures. This formula, you can use it anytime. And let's do an example. Let's say the temperature is minus 10 degrees Celsius. You know it's going to get cold again, eh? It's warm right now, but like it's around 0. But apparently we're getting the polar vortex back. So in a few days, it'll be back down to minus 20. But anyway, I don't mind. It's winter, okay? Let's go with minus 10. What's the speed of sound at minus 10 degrees Celsius in air? Well, take your little equation here, 332 plus 0.59 times negative 10. Okay, take out your calculator and just punch it in. All you have to do. So 332 plus 0.59 times 10 negative. I get 326.1 meters per second. Now, what is the speed of sound if the temperature is room temperature, 20 degrees Celsius? So there's our nice classroom temperature, let's say, well, in the room you're probably sitting in now are around 20, 332. It would be V equals 332 plus 0.59 times 20. Plug the numbers in, I get 343.8 meters per second. That is the speed of sound at room temperature. Now I could give you another example. So this is A, this is B. Let's do one more. Let's do C. Okay. What if I turned it around? What if I said, all right, the speed of sound in the room is 347 meters per second. Then, therefore, what is the temperature in the room in degrees Celsius? Well, all you have to do is use a little of your genius algebra skills. You would write 347 equals 332 plus 0.59 times T. Solve it for T. So use reverse Bedmas. First, subtract the 332. You bring that to the other side. So 347 minus 332 is 347 minus 332 is, I'm being lazy, that's 15, equals 0.59 T. Okay. Now divide both sides by 0.59 to isolate T. This is the genius algebra skills that you totally understand, right? 0.59. I get T equals 25.4 degrees Celsius. Wonderful. That's a bit warm in these parts in the winter, but there you have it. Okay, that's how you do it. So it's pretty straightforward. You're going to get questions like that, similar to that in the homework. By the way, the universal wave equation applies. Okay, so here's another example. I'll make this letter D. Let's say I have a tuning fork. Okay, and the frequency of the tuning fork is 440 Hertz. All right. I also have, I'm in the classroom. Okay, so this is my tuning fork. It doesn't really matter what it is. That's just the frequency of the sound. So here's my tuning fork. Now, also, the temperature of the air is 20 degrees Celsius in the classroom. Now, my question for you is, what is the wavelength of these waves coming from the tuning fork? We can't see the sound waves, so what would their wavelength be? Well, you would go first, the speed of sound equals 332. You do this first, plus 0.59 times 20. We already did it in one of the examples above. You get 343.8 meters per second. And then step 2, we use our universal wave equation, which is F equals lambda over V, V over lambda. Okay. Oh, I'm looking for wavelength. I'm sorry. We use wavelength equals V over F. Excuse me. Okay, I got ahead of myself there. And so that's going to equal 343.8 divided by 440 Hertz, which is my original tuning fork. And that's a universal wave equation. We've already done questions like that. It's just now they're going to give you the temperature. So whenever they give you the temperature of the air, you know that they're really giving you the speed of sound. That's what they're trying to do. Okay, so divide by 440, I get 0.781 meters, which is around 78 centimeters, of course. All right, so that's how you do speed of sound questions. Very straightforward. That'll get you through a couple, like, you know, the first sort of few questions in the homework that's assigned for today. Now, the next thing we're going to do is going to take a few more minutes for me to explain. It's a little bit more complicated. It's how we measure loudness, okay? So we use something called the Decibel Scale, and you're going to have to bear with me on this. It's a little complicated, okay? But, one more thing. There's a question in the textbook. I'm going to answer this for you now. There's a question in the textbook in the homework that says, like they say pitch. So here's the thing. We talked about pitch. Pitch, okay? Pitch is the hearing experience, the high, we call it the highness or lowness, if that's a word, of a sound. Okay, if it's high pitched or low pitched, the bass notes are low, you know, and like soprano notes are high, okay, that like that kind of thing. So highness or lowness of a sound. And here's a kind of weird thing about it. One sort of it's a bit subjective pitch, but one thing that makes it subjective is loudness. Okay? And loudness affects the perception of pitch. Okay? And so what happens is if you have a really loud sound, it can alter your perception of what the pitch sounds like. And that's the answer to that question. It doesn't say it in the textbook. It says it. I can't find it in there, but I know for a fact that's what it is. So sometimes when you're cranking a sound, it can like affect your perception of how high or low that sound actually just slightly alters it. And that is partly how your ear works. Okay. Like when a sound is very loud, it can distort the pitch in your ear. Okay. So anyway, pitch corresponds to frequency, except there's a subjective element to it. Okay, and that's the physical characteristic of the wave. Okay, having said that, let's look at our next topic, and our next topic has to do with loudness. So let me come back to this, what I had here in the beginning. I can't do this sound test with you online. I don't know if you hear these sounds or not, but what you're supposed to do with this, and you can try it yourself, it depends on how good your speaker is. Like when I play 30 Hertz on my laptop, so when I play these sounds over here, 30 Hertz, I can't even hear it. Now, maybe you're hearing that, okay? And maybe not. But if you want to try this yourself, note the website at the top of the page here. So note this website here at the top. And if you want to try this yourself at home, you can do it. Otherwise, we could try it at school if you really want to. I know I tested your hearing already. Here's the thing. Your ear does not hear sounds equally well, all the different pitches in your range of hearing equally well. We already saw today that I couldn't hear anything at all past 13,000 Hertz. Okay, and just under 13,000 Hertz seemed to be a threshold for me. I can hear that sound, but just barely. Okay, now pitch around 4,000 Hertz, I hear very well. Okay, so, and it actually sounds louder. Okay, so your ear is not equally sensitive to all frequencies, of course. Now, low frequencies are quiet too. So if I play 45 Hertz here, yeah, I can barely hear that. 60, barely hear it. 90, okay, 125. Now I'm starting to hear that. And I've got my speaker cranked on my device here, but I can barely hear 125. Now if I play the next note, oh, it's getting louder. Okay, and what I'm doing is comparing one note to the next. So here's 187 versus 250. 250 sounds louder, so I'll lower it. Now they sound about the same. Okay, it sounds about right. Maybe even lower. Anyway, trying to get them the same loudness. That's too loud there. It's pretty close to the same loudness. See, what I'm doing is lowering the ones that sound louder. That sounds about like a match. It's a good match. I made this curve earlier, so they sound about the same. See, if I played this and this, that second one is way louder, right? So I'm trying to match them. Same loudness, I think right about here. Or maybe like that. Okay, and then this. Wow, that second one sounds even louder. Okay, and then I keep working my way across. Starts getting extremely annoying around 4,000 Hertz. So here, your ear is very sensitive, right, to that. I'm sorry if I'm driving you nuts. I don't know if you can hear it or not, to be honest with you. I don't know how this app records these sounds. Anyway, okay, yeah. Now it's starting to get quieter for me. Like the 8,000 Hertz sounds quieter, so I have to raise the volume. In fact, 6,000 is already. Okay, that sounds about right. I can't, this one I can barely hear. All right, anyway, I can't hear it. Anyway, you get the idea, okay? Now, if you look at the black lines that I've drawn here, they make a, what's called a contour. So here, I'm gonna highlight it with my annotation tool. That, my friends, is called a contour of equal loudness. In other words, what I did was I moved my way through the frequency spectrum that my ear can hear. And what I found was that I really have to lower the frequency, lower the loudness of my speaker in this zone over here quite a bit. Okay, that's where my ear seems most sensitive to those sounds. Okay, and then it gets less sensitive as I go up, so I have to crank the volume. 16,000 hertz, I can't hear it even at the maximum volume. And so, now it does depend somewhat on your speaker system. Like my laptop speaker cannot reproduce 30 hertz, so it doesn't matter what I press in this zone over here, I won't be able to hear it. But this blue line, I'll trace it out again, this blue line is called a contour of equal loudness. And what it shows you is how sensitive your ear is at various frequencies. So the higher the line is, the less sensitive your ears are because you have to turn up the volume to hear the sound. The lower the line is, the more sensitive your ear is. So between 2,000 and 4,000 hertz, that's the sweet spot for your ear in terms of how sensitive your ears are. Your ears are, in a way, best at hearing those sounds. All right. Now that you've seen this, I'm going to clear this. Remember this shape, okay? Remember this shape, this contour. Now I want to show you something else. So I'm going to clear these drawings. I won't bother your ears anymore, except the sound of my beautiful voice, okay? Let's look at something called the decibel scale. Now, by the way, before we get there, okay, remember I told you to remember that shape? Okay, so there was a shape that we just did, and that shape looks something like the bottom of this colored patch here, okay? So if you go back to the picture, that line that's traced out by these squares looks approximately the same as the line at the bottom of that, okay? So you get some sense of what this graph is from your textbook. I will explain it shortly. Okay, let's talk about decibels. Now you have to bear with me. It's a little bit confusing, okay? So the decibel scale is named after somebody called Alexander Graham. You know his last name, Bell. Now, the Bell Phone Company in Canada is named after him. Okay, he didn't found that company. He moved to the States, actually. He was living in Canada, not Canadian. He was an immigrant from Europe. He worked here for a short time, and then he went and did lots of research in the United States. He invented things. I'm pretty sure he came up with devices like hearing aids, stuff like that, the telephone. So this is a pretty important person, okay, in our history in terms of his innovation, okay, things that he invented. Anyway, he worked very carefully or very extensively with sound, okay? And so when we wanted to come up with a unit to name the intensity of sound waves, okay, to describe intensity of sound waves, we use this thing called the decibel, okay, or just generally speaking, a bell, okay? And a bell is a unit of sound intensity, okay? And I will explain what a bell is. It's kind of cool. It goes by human hearing, okay, FYI. So the Bell scale or the decibel scale is tuned, the numbers are tuned in specifically for human ears, okay? So there are animals, you could score them on the decibel scale, their hearing, and they might score like a negative number. If they scored a negative number, that means they have amazingly sensitive ears, more sensitive than us, okay? So let's take a look at what the decibel scale is. Now, there's a couple of things. See, what you have to understand is sound waves are pressure waves, okay? Compressions and rarefactions. Now, the stronger the compression, the more pressure in the compression, the more it pushes on your eardrum, the louder the sound, okay? The more of a vacuum in the rarefaction and the more it pulls on your eardrum, that sound would be loud also. So compressions and rarefactions are variations in air pressure. Okay, now pressure is this thing, okay, that there's about 18 pounds per square inch of pressure in the atmosphere around your body right now. And when you create a sound with your voice, you're varying that pressure slightly, okay, in these compressions and rarefactions. So air pressure is measured in a unit called pascals, named after another scientist, last name Pascal. 1 Pascal is 1 Newton per square meter. Okay, so that's the metric way of measuring pressure. Now, your ears are amazing machines. They can detect variations in pressure as small as 20 micropascals. That's millionths of a pascal. And they can go as high as billions of pascals. So it's this amazing thing. Like between those two numbers, okay, would be 15 powers of 10. Okay, so you've got this huge range of pressure sensitivities in your ear. Now, at some point, the pressure could get so high in your ear that it could perforate your eardrum, okay, which would be like a horrible thing, but that's sound that's way too loud. So 1,000,000 billion times, like that's how much variation in intensity you can sort of hear with your ear. Now, here's the deal though. Whenever we have these huge range in numbers, we like to use what we call a logarithmic scale. Now, you don't know anything about logs yet. And to be honest with you, if I were teaching this to you in grade 11, you might not know anything about it there either because you learned it in grade 12, okay? But I'm going to explain it to you. It's a really simple concept. So before we look at the formula for how we calculate decibels, let me explain just in the margin logs. Okay, we call it logarithm, not logs like logs you build a log house with or something. Okay. Oh, I just had a bad thought in my mind about that. But anyway, I won't say it on the video. I'll tell you in class. So logarithm. Okay, spelled like this. Let me show you how logarithms work. Really simple concept. Okay. Here, let's see if you can see a pattern. Log is a mathematical function. Okay, it's a mathematical function. What does it do? Let me show you what it does. Okay, the log of 1 is 0. Okay, the log of 10 is 1. You could try this on your calculator if you want. It has a log button. Try it. You don't believe me? Try it. Enter the number 1 and press log. See what you get. You'll get 0. Okay, the log of 100 is 2. The log of 1,000 is 3, okay? And the log of 10,000 is 4. Now, do you see the pattern? All right, well, these are all powers of 10. Let me write them a different way. The log of 10 to the power of 0, any number to the power of 0, you'll be learning this in math class, any number to the power of 0 is equal to 1. So that's equal to 0 here. The log of 10 to the log of 1 is 0, right? Now, the log of 10 to the power of 1, 10 to the power of 1 is just 10. Okay, so here, these are all equivalent. 10 to the power of 1 is 10. It's equal to 1, right? Now, the log of 10 squared is 100. Okay, so we know that that's 2. And the log of 10 to the power of 3 is 3. That's 1,000. And the log of 10,000 is 10 to the power of 4. It's 10,000. It's 4. So what does a log do? Well, it just tells you what power of 10 you have. Isn't that brilliant? It tells you what power of 10 you have. So why am I telling you this? Well, it's because the decibel scale is based on powers of 10. Okay. It's based on powers of 10. And you calculate it using this log function. You're not going to need to use a calculator or the log button on your calculator for this though. It's actually way easier than that. Okay, and I'll show you that in a moment. But my point is this is what the log button does. It tells you how many powers of 10 there are in your number. So based on this pattern, what's the log of 1,000,000? That's 10 to the 6. Well, it would be 6 because you have, so if I were to write it like this, the log of 1,000,000, you would get 6. Okay. Basically, it tells you how many zeros there are, right? There's 6 zeros there, 6 powers of 10. That's it. That's what the log function does. Isn't that cool? You just learned some grade 12 math. You just did. Now, you're not going to have to do anything weird with it. Don't worry. But you see, what log does is it tells you what your exponent is. So it's a very useful thing, okay, when you're doing some certain types of math. However, for us, all we need to know is that it gives us whatever the power of 10 happens to be, okay? And we're gonna, now we can go and look at what the decibel scale, how that works. Okay, so let's go ahead and look at it. Okay, pardon my yawning. It's past my bedtime, it always is. All right, so here's the deal. We measure sound intensity in a unit called watts per square meter, okay? Now, watts is energy, right? It's joules per second, okay? And a square meter is like, let's say the tables at school are about 2 square meters. So if a sound wave is carrying, 5 watts and it's divided over 2 square meters, that would be 2.5 watts per square meter, okay, when the sound wave hits the table. Now, your eardrum is very tiny, a very small surface area. You can measure it in square meters, though. It would be small fraction of a square meter. But you get the idea. It's energy, the rate of energy impacting a square meter of surface. That's how we measure sound intensity. Now, what is this number here? 10 to the negative 12. Well, 10 to the negative 12 is a really small number. Now, if you don't understand negative exponents, I'm sure we went over this in science class before, but 10 to the negative 12 is actually equal to 1 over 10 to the positive 12, okay? And that is equal to 0.0000000000001, okay? A really tiny number. So that is a very, 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 very small number. It's basically 1,000th of a billionth of a watt per square meter. Okay, really, really small amount. Now that happens to be the quietest sound that your ear can hear. So this is called the threshold of human hearing. That's the threshold. You can't hear quieter sounds than that. That is the softest sound your ear could possibly hear, okay? So that is a special number, I'm gonna highlight it, for humans. Now, if there was something quieter than that, maybe some other animal could hear it, okay? There's definitely animals out there that have better hearing than us, more sensitive, let's say, like bats and so on. Okay, if you use sonar to get around, you would need more sensitive ears, like that's how it works. But here's the thing, for humans, this is our most sensitive, this is the softest sound you can hear, has that intensity. If you had some smaller number, something less than that, that doesn't mean you don't have any sound. Of course, you do have sound, you just can't hear it. It's too soft for you to hear it. Your ear just not sensitive enough to respond to it. So it's as if there's no sound. Okay, so that is the threshold human hearing, okay? We call it I0, the bottom line, the quietest sound you can hear. Now, the way we calculate a decibel, so we use a small d and big B to represent decibels. So here you see it here, dB, okay, little d, big B. So bell is the unit of sound intensity. Decibel means okay, 1 bell would be 10 decibels. Think of it like this. A decimeter is 1/10 of a meter. So a meter is 10 decimeters. It's kind of a weird unit. We hardly ever use deci, but we do it for decibels, okay? So here, what's happening is the decibel scale works like this. You take the intensity of the sound that you're hearing. So this is the sound that you're hearing, okay, I. And this is the threshold of human hearing, the 10 to the negative 12. Okay? And what you do is you divide those two. And then when you take the log will tell you what kind of power of 10 you have inside the brackets there. Then you multiply it by 10, you'll get the decibel scale. Okay? Now let me give you an example of this. Okay, and I'll show you what I mean. Let's say, okay, so here's an example here in the margin. And I know it looks complicated. Please don't worry. Like, I'm going to make it easy for you, but I'm doing my best for you to try to understand it. Okay, so I hope you're paying attention, because I like it when students understand things, and you can understand this. Yes, it's something you learn in grade 12, but not everything you learn in grade 12 couldn't have been explained to you at some earlier age. This is not hard to understand. Just follow along here with me for a second. Let's say the sound you were listening to had an intensity, okay? Let's say I was equal to, I don't know, the quietest sound you could hear, 10 to the negative 12, okay, watts per square meter. And that's the sound you can just barely hear it, right? You're in a totally quiet room and you hear this rustling or something, some like movement, and it's a very, very, very quiet sound just at the threshold of your hearing. Well, that's 10 to the negative 12 watts per square meter, right? All right. Well, we know that the threshold of human hearing is also 10 to the negative 12 watts per square meter. So how many decibels would that be? Well, let's use the formula. The number of decibels would equal 10 times the log of the ratio of these two numbers. Now, you would go 10 times the log. Now, what's 10 to the negative 12 divided by 10 to the negative 12? Well, it's the same number, so they cancel out. And you get 10 times the log of 1. Because when you go a number divided by itself, you get 1. Well, what's the log of 1? Well, the log of 1, I already told you in this little chart here, is 0. So when you're listening to the threshold of human hearing, just the quietest sound you can possibly hear, that turns out to be 0 decibels. Okay, so 0 doesn't mean 0 sound for decibels. 0 decibels is the quietest sound your ear can perceive. So this is the threshold of human hearing, okay, in decibels. 0. That's easy to remember, right? 0 is the quietest sound you can hear. It doesn't mean there's no sound. It doesn't mean 0 sound. So please get that out of your head. It means it's 10 to the negative 12 watts per square meter. It means it's a really quiet sound. Now, what if we increase the volume? What if we turn it up? Let's say you put on your AirPods or whatever you call those things, stick them in your ear and you crank the volume, and now you're getting, I don't know, a much louder sound. Let's say 0.01. Here, I'm going to write it like this. What if here's another example. What if I was equal to 10 to the negative 2 watts per square meter? How much is that in decibels? Well, therefore, dB would equal, okay, now watch carefully, 10 times the log of 10 to the negative 2 divided by 10 to the negative 12. Now, the rule for dividing powers with the same base is you subtract the exponents. So it's going to equal 10 times the log of 10 to the negative 2 minus negative 12. Well, what's negative 2 minus negative 12? Okay. Well, when you subtract a negative number, you add. So negative 2 plus 12, okay, is 10. So this is equal to 10 times the log, times the, oh gosh, I'm having a hard time here. Okay, so 10 times the log of 10 to the power of 2. Now, what does the log function do? Well, it tells you what the exponent is, right? So the log of 10 to the power of 2 is 2. So I'm going to get rid of this whole thing. This whole thing is replaced by the number 2. So it's just 10 times 2. Okay? Oh, no, wait. I'm sorry. I made a mistake. Pardon me. I did my exponent wrong. -2 minus -12 is not 10. It's not 2. It's 10, actually. -2 minus -12 is the same as -2 plus 12. That's 10. I apologize. Okay, it must be getting late at night for me to do that. It is. It's 10:16. So yeah, that's late for me. All right. Now, anyway, so this is equal to, pardon me, 10 to the power of 10. Well, the log function just tells us what the exponent is. The exponent is 10. So this is just 10 times 10. 10 times 10 is 100 decibels. Okay, so long story short, and I know that it's confusing when you first see this log thing, but the log thing just tells you like how many powers of 10 are in your number. Works for negative powers of 10, for positive powers of 10, whatever you want, okay? And so what we're doing is we're using this logarithmic scale, which means it's based on powers of 10 to calculate the decibels. Now I've got a chart for you, okay? So let's say you found that whole calculation very confusing. No problem. I'm going to make it easier for you. So let's look at this chart just for a moment. It's kind of interesting. Okay, so this is a decibel scale. So 0 decibels right here at the bottom. That's the threshold. That's the quietest sound the human ear can hear. Now, 10 times louder than that, 10 times louder than that is 10 decibels. Okay, so that's 1 power of 10 higher than the 0 decibel thing. Okay, that is the sound of someone breathing in a quiet room. Let's say you're in a quiet room right now, you just breathe. Okay, breathe by yourself, quiet room. That's 10 decibels. Okay, now you go to Algonquin Park and there's whispering, it's very quiet, so maybe some leaves rustling in the distance. That's about 10 times louder than the breathing, so that's 20 decibels. 10 times louder than that, 30 decibels. Okay, and that will be like a quiet rural area, like out on the farm somewhere. There's not a lot of noise going on. A library with nobody talking, but the fans running in the background would be 40 decibels. Now we're talking every time you go up 10 decibels, it's 10 times louder than the previous one. So this is 10 times louder than 0. This is 10 times louder than 10 decibels, another 10 times here, another 10 times here, because the scale is based on powers of 10. So 40 decibels is actually 10,000 times louder than 0 decibels. Okay, but it's still pretty quiet. It's a quiet room, okay, in the library. That's 40 decibels. All right, when you're writing a test in the classroom and all you can hear is maybe a fan or something like that running, that's probably around 40 decibels. Okay, so you're living in the suburbs in Orleans, but it's at night, there's not much going on. Maybe you're just having a conversation with your parents in the house, unless you're yelling at each other. That's around 50 decibels. And again, that's 10 times louder than 40. A conversation in a restaurant, so playing music in the background, getting up to about 60, depending on the restaurant. Some of them crank it high and you can't hear yourself, then that's a higher decibel count. But in a nice restaurant where they play the music softly so you can talk, yeah. All right, turn on a vacuum cleaner, or you're standing next to the Queensway at a distance of about 45 feet. Okay, and now it's starting to get annoying. See that? Starting to get annoying around 70 decibels. Not harmful, just annoying to constantly hear it. Okay, a freight train going by 15 meters is 10 times louder, okay? So if you're exposed to this constantly at 80 decibels, you're gonna get hearing damage. Okay, if constantly, not instantly, just over the long term. So you don't want that kind of loudness in your ear for long periods of time. All right, a blender or a truck at close range, 90 decibels. If you're exposed to that for 8 hours, and it doesn't have to be 8 hours in a row. It could just be like an hour here, an hour there, like it adds up. Okay, so 90 decibels is loud enough, okay, that you can have some minor hearing loss if you're exposed for long enough. Now, 100 decibels, you're starting to get dangerous. It's starting to become serious, your hearing loss, okay? And if you think a jackhammer, that's extremely loud, okay? A jet taking off, if you're on the tarmac and you're one of those guys directing the aircraft, okay, to where to park, those jet engines are extremely loud. If you're 300 meters away from them, that's pretty far. That's like 1,000 feet away, but still, it's going to be damaging to your ears, okay, even at that distance. All right, a car horn, if you put your ear right against the car, okay, and somebody sounds the horn, 110 decibels, that's going to sound quite loud. 10 times louder than that, a chainsaw at close range, and actually it'll sound painful to your ear. You'll wince at the sound at 120 decibels. A jet takeoff at 100 meters is 130 decibels, and of course that's going to cause damage. An aircraft carrier deck, here you're very close to the aircraft. It's not like on an airport where they're kind of far away, the operators, from the planes taking off. Here you're right next to them. That's incredibly loud. You must wear protection for that, okay? And if you crank your AirPods at their maximum level, you're taking a chance, okay? Anyway, the jet taking off on the aircraft carrier deck, 150 decibels. That will perforate your eardrum. Your ears will bleed, okay? 160 is instant perforation. And so it's just as soon as you hear that 160, like an explosion or something, the sound, just the sound of the explosion, it reaches your ears and your ears start to bleed. Very bad deal. Okay, anyway, that's the decibel scale. Now, let me, on this chart, make your life super easy. What I'm going to do on the chart is I'm going to write next to it what the intensity is. Here at 0 decibels, the intensity of this sound is 10 to the negative 12 watts per square meter. Okay, that's the threshold of human hearing. Here, it's 10 to the negative 11, okay, at 10 decibels. Here, it's 10 to the negative 10, 10 to the negative 9, okay? Every time you go up 10 decibels, you are increasing the loudness by a factor of 10, okay? This is 10 to the negative 8, 10 to the negative 7, 10 to the negative 6, okay? 10 to the negative 5, 10 to the negative 4, okay? You see the pattern, negative 3, 10 to the negative 2. We said 100 decibels was 10 to the negative 2. Remember our example? Look at that, 10 to the negative 2. We used the formula. How many decibels did we get? We got 100 decibels. See, I'm not lying, okay? I'm not lying. 10 to the negative 2 for 100, 10 to the negative 1 for 110, 10 to the 0 for 120. Now, 10 to the 0 is not equal to 0. It's 1 watt per square meter. That's a very loud sound, okay? Here, 10 to the 1. So that's 10 watts per square meter, 10 to the 100 watts per square meter. And finally, 1,000 watts per square meter is insane loud, insane loud. Like you've never heard a sound that loud, otherwise you would have perforated your eardrum. So you need to wear ear protection if you're going to be exposed to anything close to that. But that's it, okay? All right, so now let's turn the page. And a point that I wanted to make to you is, so we have the decibel scales, but your ear is not equally sensitive to all the frequencies, right? So you can have a sound that is intense, that's very intense. So for example, you could have a sound, let me go to the other end here. Actually, let me go back to my app. I can crank 16,000 Hertz. I can crank it. I can give you a sound 150 decibels at 16,000 Hertz, but it won't perforate your eardrum, okay? Why doesn't it perforate your eardrum? It's because your ear is not sensitive to it. So it's a really annoying sound for the dogs maybe, okay? But since you can't hear it, then it will not damage your ear because your eardrum is not resonating with that sound. So, okay, that is an example. There's a question like this in your textbook, listen carefully. That is an example of a sound that is intense, but not loud. You get it? So in other words, if we pick a frequency that you can't hear, we can crank the volume, and that's a very intense sound wave, but you can't hear it, so it's not loud, okay? So also at 30 Hertz, you can crank it at 30 Hertz, you won't hear it. Well, not, at least not very well, okay? And so that's another example of a sound that's intense but not loud. Okay, so that's one of the questions in the homework, and that's how you do it. Okay, let's go back to the OneNote here. Now, what is this graph all about? What are they talking about here? All right, well, what we're saying is, okay, let me erase my little red line. Okay, what we're saying is, let's say you have a sound at 20 decibels, or sorry, not 20, 20 hertz. 20 hertz is that is a frequency right at the bottom of your hearing ability. How loud do you have to make the sound so you can hear it? So let's say I set my speaker to emit 20 decibels. Will I hear it? And this graph is telling me I will not hear that. In fact, I have to go all the way up to here where the blue patch starts before I can hear the sound. So what it's saying is at 20 hertz, you would have to turn it up to 100 decibels minimum, not 160, but 100 decibels minimum to hear the sound. Now, what about at 200 decibels? Let's go up to 200. So at 20, you have to crank it to 100. At 200, I go up here at 200 hertz. I have to turn the volume up to 20 decibels. So my ear is much better at 200 hertz at hearing the sound. So I can lower the volume to 20 hertz and I can hear it. Okay, so at 200 hertz, I can lower it to 20 decibels minimum to hear the sound. Okay. You understand what the chart is trying to tell you? So where is your ear the most sensitive? Well, it's actually right there. Right there where that blue patch is lowest. And you can actually, you don't even have to go to 0, like it's even better than 0 decibels. So that is around 4,000 hertz in frequency right there, 4,000 hertz, 4,000, not 400, 4,000 hertz. And is your most sensitive. Your ear is best at hearing sounds at 4,000 hertz, okay, where the graph goes the lowest. Now, human speech, you're hearing the sound of my voice right now. Human speech, if you were standing like a few meters away from me, I would be speaking between 100 and it depends on how low my voice is, okay, but like for men, somewhere around here, okay. For women, it's somewhere like up here, okay, for your speaking frequencies, okay? And we typically speak somewhere between 50 and 80 decibels, okay, in loudness. So that's how loud we are, between 50 and 80 decibels when we're speaking, okay? But we also vary in pitch. And so people's voices, my voice is roughly around 240 hertz. So this is Mr. Flynn would be in there. That is the frequency of my voice, Flynn. 200 hertz, and I probably speak at around 60 decibels, maybe less if I use my microphone. But the speaker will amplify it to higher than that, right? So you can all hear it. But you see what the graph is trying to tell you? It's trying to tell you where your ear is most sensitive. So that's where the low mark is on the blue patch. And generally speaking, how well your hearing works across the whole spectrum. Okay. All right. So let's see if we can answer some questions. I'm going to do a couple of these with you, but only a couple, and you can do the rest. So let's go ahead and do this question here. Convert the following intensities to decibels. Easy peasy, watch. It's 10 to the minus 3 watts per square meter. Am I going to take out my calculator? No. All I have to do is go back to the chart because I helped you with this. Look up 10 to the minus 3. Okay, so I'm going to circle it in red. The bottom one is 10 to the minus 12, so I put the frequencies right there. I go up, minus 11, minus 10, minus 9, minus 8, minus 7, 6, 5, 4, 3 is right there. And so that corresponds to 90 decibels. And so I go back here, I zoom in on this. This would be 90 decibels. Okay? So that's how you do that question. I'll let you do the rest. Now, what about convert these to watts per square meter? Well, How intense is, can you do the opposite? So how intense is 50 decibels? Oh, super easy. I go back to my chart. Okay, 50 decibels would be right here. 50 decibels, that corresponds to 10 to the negative 7 watts per square meter. So, pardon me, oops, that was a mistake. Okay, so here, I'll scroll down. So this would be 10 to the negative 7 watts per square meter. There you have it. Oh, now 3 bell, by the way, I'm just going to say here, note on the margin, 1 bell, deci means a tenth. So 1 bell is 10 decibels. So if you were doing 3 bell, you would convert that first by multiplying it by 10. That's just 30 decibels. Then go ahead and use your chart. 8 bell would be 80 decibels. All right. Now, let's look at question number 2 for a moment. So I've done like one question from 1 and 2. This is supposed to be number 3, pardon me. So how many times louder is 120 decibels compared to 60? Well, let's use our chart. We're almost done, by the way. So 120. 120 is 10 to the power of 0. See that? 60 decibels is 10 to the power of negative 6. How many powers of 10 are between those two? Well, one way of thinking of it, if you don't like what I'm doing here, start at 60. Every time you go up 10 decibels, it's 10 times louder. So from 60 to 70 is 10 times louder. From 70 to 80 is another 10 times louder. 80 to 90, another 10 times louder. 90 to 100 is 10 times louder again. 10 times again, and then finally one more jump to 120 is 10 times again. Now, how many times did I do that? Well, I did it 1, 2, 3, 4, 5, 6 times. So is therefore 10 to the 6. 6 powers of 10 louder. So this would be, the answer would be 10 to the 6 times louder. Now you should be able to do the rest there. And we have one question left. Using the above graph, so that's this chart that you're seeing, what is the minimum loudness necessary to hear a sound at 200 Hertz? So 200 Hertz, you go up here, you look up 200, you go up to the bottom of the blue colored patch, okay? Put a little dot, I know I erased it, but I'm just repeating myself. Then go over to the decibel scale on the y-axis, 20. So the answer here for the first question is 20 decibels. Okay, and that's it. Okay, so let's take a brief look at the homework. I want you to finish this sheet, only takes a few minutes. Please don't tell me Ada, okay? That's gonna take you hours. Actually, it's not Ada listening to this today, so. Trying to think of who in your class. Lauren, okay? Don't tell me it takes you 6 hours or anything like that. I'm just kidding. Okay, it was actually the other guys that were saying it takes 6 hours. You can't spend 6 hours on these one-step questions. If you don't know what you're doing, you're staring at the page for 6 hours. Well, you're not really doing anything, are you? Okay, you should ask for help and not waste time. Now, let's go to the homework outline and let's see what we got accomplished here today. So we talked about frequency and pitch, so that's done. We did decibels and loudness, we just did that. We did speed of sound at the beginning, so that's all taken care of. So you also have this homework to do, and we're going to hold it there. Also, please don't forget that you have a test on Monday, okay? And the test on Monday only goes up to lesson 5. So I'm going to put test goes up to and including 5, okay? So test, their first test, or quiz, whatever you want to call it, whatever makes you feel better, okay? 1, 2, 3, 4, and 5, and that's all. So what the material we did today is not on the test. It'll be on the next one, okay? At the end of next week, we'll say. So that's it, guys. Very good. Okay. enjoy your homework. I mean, I enjoy giving it to you, like I say, and I'm sure you enjoy doing it. I mean, I just love imparting this information to you. Isn't it so cool? Now you know what a decibel is. You know how that works. You know how logs work too. You can impress your friends and family with your amazing knowledge, okay, of these things. Go up and tell your dad, your mom, Dad, what's the log of 1,000? And you can say 3, okay, because you know it's 3 powers of 10, and log tells you how many powers of 10 you have, right? Now, what about the log of 0? Well, you know that's 1, because 10 to the power of 0 is equal to 1. And you know, you're just going to blow them away with your amazing knowledge and expertise. You know, and then you can tell them about some of the other things too, what you learned about loudness. And tomorrow we're going to do Doppler shift. Or not tomorrow. Yeah, tomorrow when you're in class. You're going to love that. Lots of stories to tell your parents there. Okay. So enjoy your afternoon, and I will talk to you soon. Please note, help each other out with the homework. That's great. Keep doing that. If you get stuck, please note that I can't be on the group chat all the time. I'm in class all day long and making these lessons and stuff, and I don't have a ton of time. Not like I did in the first semester when you were the only class I had. So keep that in mind. Help each other out. Wonderful. And if everyone gets stuck, of course I will help. Okay. So have a good day. We'll talk to you tomorrow.